In this video, we're going to define a topological space. So as we were studying metric spaces, we saw that many important concepts could be defined in terms of arbitrary open sets without referring to a metric d or a distance or open balls or anything like that. So for example, the definition of a limit point of a set and the limit of a sequence and whether a sequence converges, each of those ideas could be defined only in terms of open sets without referring to distance between points. Similarly, we can define interior, closure, and boundary of a set in terms of open sets alone. And even continuity can be defined in terms of open sets. So our initial definition of continuity is this epsilon delta definition of continuity that is clearly based on distance. However, we saw that that was logically equivalent to a function is continuous if and only if for any open set V in the codomain, the inverse is an open set in the domain. So each of these ideas can be completely defined in terms of open sets. Also, working with the distance function can be awkward or overly technical. For example, if we think about just the standard distance between 2 points x and y in the real numbers to the nth power, like that is the square root of the sum of xi minus yi squared from I equals 1 to n. And anytime we have to do proofs involving this specific distance, it's just going to get, as I said, kind of annoying or awkward or technical. And so framing these ideas in terms of more general open sets can make some of these definitions, concepts, and proofs more elegant. So we're now going to define a more general kind of space called a topological space, which does not rely on distance or a metric. And everything that we prove in this more general setting will also apply to metric spaces. So this is a very important definition. Basically, we're going to be using it for almost the entire rest of the course. Here we go. Let X be a set and tau be a family of subsets of X that satisfy the following definitions. The set X and the empty set are elements of tau. The union of any family of members of tau is also a member of tau. And the intersection of any finite family of members of tau is a member of tau. So I just have an italicized T here, but I really would have rather written this tau. So it's a Greek letter T, but that's typically what's used for a topology, tau. Then tau is a topology for X, and the members of tau are called open sets. The ordered pair X comma tau is called a topological space. So basically, tau is a collection of sets, and we are saying right up front, here's X, here's the collection of subsets of X that are open. So we can also think of a topology as defining the open sets of X. So we could alternatively state this definition, and either way is fine, but sometimes one is more natural than another depending on the context. We could also state it as a collection of subsets of X is a topology for X if both X and the empty set are open sets. In other words, in tau, in the topology, the union of any collection of open sets is an open set, and the intersection of any finite collections of open sets is an open set. So tau, the topology on X, is the collection of open sets. Now note that we proved that these properties are true about open sets in a metric space. So we proved that in any metric space, it's always true that the entire set X and the empty set are open. It's always true that the union of any collection of open sets is also an open set in a metric space. And it's true that the intersection of any finite collection of open sets in a metric space is itself an open set in that metric space. Therefore, the open sets in any metric space XD form a topology on X, and therefore any metric space is also a topological space. So metric implies topological space. The open sets in a metric space are a topology on the set X. Now, also note, in a metric space XD, we started with a set X and D, a distance or a metric, and we used that metric to define what the open sets were or figure out what the open sets were. We said that a set U was open if it was a union of open balls, and those are balls X comma epsilon with the metric D. And we said that that was the case. U was open if and only if for any point in U there is some epsilon greater than 0 such that the ball centered at X of radius epsilon is contained in U. So these were equivalent definitions of being open in a metric space. But again, in a topological space, we're completely skipping the idea of distance completely. So we are defining the space by saying what the open sets are. And the topology on X is the set of sets that are open in X. So to show that a collection of sets tau is a topology on a set X, we need to show that the set X and the empty set are elements of X, that the union of any family of members of tau is also a member of tau, and that the intersection of any finite family of members of tau is a member of tau. So, and to show that the collection of sets tau is not topology, we can show that any of the above properties are false. So let's do an example. Let's let X just be the 3-element set A, B, and C. And we've got 2 different collection of sets, S and Y. So for each of these, I would like you to either prove or disprove that that collection of sets is a topology on X. So is S a topology on X? Is Y a topology on X? I'm going to pause and let you think about that for a moment. Okay, so first we've got our set S. So we have 3 properties to check or prove. So first of all, the empty set and the entire set X equals A, B, and C are elements of the set S. Great. Secondly, is it true that arbitrary unions of elements of S are in S? So we could first note for any set A, A union the empty set is just A, and A union the entire set is just the entire set. So we don't really have to think about, unioning the set X or the empty set with the other ones to worry about those. So we could just worry about the other sets other than the empty set or the entire collection. And so the only other sets we really have to be concerned about then are B union BC. And what is that? That is the set BC, which, yes, that is an element of S. So, yes, it meets the property that for any sets in S, their union is also in S. Here, X is a finite set. There aren't that many sets to be concerned with. So that's all we have to do in this particular case. Now for part 3, let's see. Again, we can observe something similar to this. For any set A, A intersected with the empty set is the empty set. A intersected with the entire set X is the set A. So we really, again, only have to think about the sets that are not the empty set or the entire set. And again, there's just 2 sets to think about in this very small example. So the only sets we need to worry about are B intersected with BC, and that is the set B, which again, we see as an element of S. And so we see that, yes, S is a topology on X. All right, next we've got the set Y being the empty set, the set containing A, the set containing C, the set containing B, and the set containing A, B, and C. So the first criteria is met, the empty set and the set X equals A, B, and C are both elements of Y. The next criteria, is it the case that arbitrary unions of elements of Y are in Y? Let's see. So the set containing just A and the set containing just C are both elements of Y, but the set containing A and C is not an element of Y. So we see that, and that would be A union C is the set comma AC. So we see that arbitrary unions of elements of Y are not in Y. Therefore, unions of elements of Y are not necessarily in Y. So Y is not a topology on the set X.